We were talking about eccentricity. Eccentricity. I told you that when we locate our column, the location or the point of action is important. Depends on this point of action. This point of action will see different behaviors. Okay, but in some conditions, uh, we may we may not be capable of be able to put the column exactly at the center. So sometimes we may have eccentricity. This eccentricity can be either one directional or two directional. Right now we're talking about right now we're talking about uh, one directional eccentricity. What was uh, the result of eccentricity? So if you remember, I told you that when everything is at the center, when the forces are at the center, the stress distribution, or will have uniform stress distribution under the foundation. Okay, but when there is an eccentricity, the stress distribution is no longer uniform like this. Um, Once I found the distribution for you in the in its main method, you saw that it takes time, and also you need to know many factors if you want to find the exact distribution like this. Uh, but instead of this distribution, you can use another distribution like this. What's the difference? The difference is that instead of using a foundation with the width of b, you consider a foundation with width of b prime. In this foundation, in our main foundation or in actual foundation, the force is not at the center, okay? But in our imaginary imaginary foundation, the width is b prime and the force is in the middle of this foundation. So if we assume that these foundations are equal, so we can follow our previous equations. Okay, what's the difference? The different part is here. Okay, the different part is here. This term should be our new depth, b prime. Understood? So again, the actual stress distribution under eccentric load is something like this. And as I said, because it's not easy to uh, generate new formulations like this for this case, okay, because all we had so far like these shapes, for example, factors, all these formulations that we had so far uh, are generate for this type of distribution. And if we want to go with this distribution, we need to regenerate all the formulations again. We need again new failure surfaces. We need many other factors. So instead of doing this difficult and complicated work, we use an assumption. What is this assumption? The assumption is that this behavior, this actual behavior, are somehow like this behavior. Okay, so we're gonna in this assumption we uh, neglect this part of the foundation. We assume that instead of, for example, a foundation with the dimension of b and l, instead of this we use a smaller foundation with the dimension of b prime and l. But the stress distribution in here is uniform. Okay, so uh, the eccentricity of the load pays off by is paid off by this assumption. Okay. Any questions so far? Everything is clear.
Teacher, if we calculate Q, we have to calculate it is a B prime or B.
Everything is B. I mean, when you want to find, for example, factors, shape factor, depth factor, everything is based on B.
Mm-hmm.
The only difference is here. Just one uh, difference. Okay, I'll show you in the examples. Okay,
Okay.
so let's solve an example. Let me find it first. Here, look at this. In example 4.7, a continuous foundation is shown in figure 4.23. If the load eccentricity is 0.2 meter, determine the ultimate load Q per unit. Look at here. What is asked? What's asked? Ultimate load, not stress distribution, not anything, not allowable load. Okay, ultimate load per unit length of foundation. Use Meyerhoff's effective area method. Okay, what was the name of this method? Meyerhoff effective area. So this method is called Meyerhoff effective area. And what is B prime in this method? B minus 2E. Okay, from figure 4.23. Okay, this is our figure. Um, in this figure, you can see that the soil type is sand. Okay, the soil type is sand. So even if this part C prime is equal to 0 uh, wasn't here, you should consider C 0. Why? Because in sand doesn't have any what cohesion. Uh, for example, what is sand? You all, for example, you have been all of you, I think, have been at a beach. Okay, uh, if you feel the sand near the beach, you can feel that there is no cohesion inside that type of soil. So uh, whenever you see sand, you should consider C as 0. And once we talked about it, when C is 0, there is no need for what? For NC and C term in general. Okay, let's check the other parts. Phi prime is phi prime is 40 and gamma is 16.5. Okay, so look at here. What's the difference? Everything is same except for phi prime. And let me see why it says gamma prime. Let me see if there is any water. Gamma is 16.5. Okay, it's okay. So again, in the general shape of the equation, we have C and C blah blah blah. But because C is 0, all the final answer of this term would be 0. So there is no n for this term. Okay, NQ and N gamma from the table 4.2. Okay, from the table 4.2, we can see that N gamma is 109.41 and NQ is 64.2. Okay, so you all know how to get these factors. The important part is here. B prime is equal to 2 minus 2 B prime is equal to B minus 2B. When you talk about when you talk about E, you should pay attention to the units. The units, all the units in here are meter, so there is no need for any conversion. 2 minus 2.2, and the answer is what? 1.6. Okay. The next part is to find these factors. This one, this one, and this one. The first one is shape, depth, and load inclination. As you can see, there is no inclination here. So the load is perpendicular to the surface. So this term is 1, and this term is 1 as well. Okay. All you need to find is what? Shape factor for Q term, shape factor for gamma term, depth factor for Q term, and depth factor and depth factor for gamma term. Okay. In chapter 4.3, from chapter 4.3, we can get all these equations. Let's have a look to this chapter, to this table. This chapter, in this table, what was the, let me check it again. In here, D is df is 1.5 and B is 2. 1.5 divided by 2. So this is more than 1 or less than 1. Less than 1. And 5 is 40. So let's have a look. As I said, df over b is less than 1 and phi is more than 0. So we should pick this one. As I said, C term C term is not required. And gamma term is 1, hopefully. All we need to find is Q term. df over b. df over b. 1 minus sine okay, let me write it here. So it would be 1 plus 2 the tangent of 40 multiple 1 minus sine of 40 divided dot df over b 1.5 over 2. Let's see the solution. Do not make this mistake. In here you should use b, not b prime. Okay, we just need to use b prime just for one time. And where is that? Okay, we need to use b prime here. Okay. So this factor is 1.60. Let's go for shape factor. Shape factor again. So for the shape factor, phi is more than 0. Phi is more than 0. Sorry, shape factor is 0. This one is not required because it's C factor. And for this one, if we use this, we can get our numbers. 1 plus 2 divided by what is I need to tell you something before that. If you check the question, it says that the foundation there is a continuous foundation. What does it mean, continuous? Okay, continuous foundation means this. This is continuous foundation. What's the difference in continuous foundation? For example, once you have, suppose that you have a square foundation, BL. B is 2 meter, L is 2 meter. What is BL ratio right now? 1. Suppose that you have a rectangle foundation like this. 2 and L is 4. What is B over L right now? 1.5. In the third case, suppose that you have a foundation like this. 20 and 2. What is B over L right now? 2 divided by 20. And it's 0.1. Okay. In the last case, for example, you have 2 meter, B is 2, L is, for example, 200. What is B over L in this case? 2 divided by 200, it's 0.5. In the continuous foundation, L, the length of foundation, is much, in all cases, L is more than B. But in continuous foundation, L is much bigger than or much longer than B. So in this condition, we neglect B over L. For example, in our calculation, when we got a 0.01, we can consider this as 0. Okay, understood? So whenever you see that the foundation is, or there is a continuous foundation, B over L can be considered as 1. Okay, P over L can be considered as 1. So far, you understood. So far, you learned two things. First, whenever you see sand, C is 0. Whenever you see continuous foundation, B over L is 0. Okay, B over L is 0. So here, FQS. When you want to find B over L, or when you want to find FQS, you should use B over L ratio. So this one is 0. Again, this one is 0. So look at here, because the foundation in question is a continuous foundation, B over L is 0. Hence, shape factor for Q term and shape factor for gamma term are 1. Okay, so for this equation, NQ is now, this one is 1, this one is 1, this one is 1, we got this one 1.16, 1.16, this one, and the rest of them were 1. So B and gamma. Okay, so everything is clear. What is this? This one is Q. What was Q? Gamma dF. dF is 1.5 and gamma is 16.5. Okay, so this is Q. Q and Q, shape factor, depth factor, node inclination factor. This one 1 over 2 gamma. What is this? The point is here, B prime. If I give you this type of question in an exam, this part, that means considering B prime instead of B, would have a considerable mark. Okay, considerable portion of your mark would be for this one, because the rest of it is the same. And this one is n gamma and the factors. Understood? And the last thing. Okay, last thing. As I said, we are looking for QU, not for Q. What's the difference? QU is another important point. B prime, or let me write it this way. A prime dot Q. What is A prime? B prime dot F. Okay, B prime dot F. So to find QU.
Teacher.
What?
Yeah, now I haven't screened before. I don't know why. It depends on me or not. I don't know. But now I get the screen. Can you show again? What did you do?
This part, can you see it now? Can you see the screen now?
No, it's a black page.
What about the rest of you?
We can see, sir.
What now?
I can see.
You can see now?
No. On the black page. Now it's
Okay.
coming.
Okay.
Just write something. I don't know. It's a picture or video.
just wrote this. If you can, if you still have, if you still have problem, you can leave the class and join again. Okay, I just told that to find QU, you should use B prime and L prime. Okay. B and L. In our case, B prime is 1.6 and B is 2. And because the foundation is continuous, we're not going to find the capacity for the whole foundation. If you check the question, you'll see that you should find the capacity per unit length. What does it mean? It means L is 1, okay, per unit length. Because as I showed you, the foundation is lined. So instead of finding the capacity for the whole foundation, we just pick one part with the unit length of with the unit length of 1, and we found the capacity for this. Any question? Everything is clear? Okay, so let's talk about the second method for eccentric loading. So far we talked about effective area method or Meyerhof effective area. So generally I'm going to talk in this for this part because it's very common and you should use it in the future. Generally we have two methods. The first one was effective area method. What was effective area method? B prime. And it's equal to B prime. That's what was B prime? B minus 2B. Or in case of this one, LA minus 2. So far we just talked about one main eccentric loading. And the second method that I'm going to talk about it is the reduction factor method. What is this? I told you that, for example, the main distribution is this. And for effective area method, we consider that foundation is something like this. Okay, with a uniform distribution but smaller widths. However, the reduction factor method, instead of reducing the width of the foundation, considers this. So in reduction factor method, the main distribution is something like this. And instead of reducing the width, and again we consider this distribution, but here we got QU, here we got R dot QU. Okay, instead of reducing the length or the width of the
Teacher,
foundation, what?
my screen are gone. Can you do it again? I don't know what is happening.
Maybe because of your internet.
Just it is freeze and then go.
Okay, instead of reducing the width of the foundation, we reduce the capacity. So in this case, we have effective, or we have a new capacity R dot Q. What is R? R is a reduction factor. How can we get it? In here you can see a reduction factor method for granular soils. What does it mean for granular soils? It means for sand, not for clay.
Teacher, I can't see anything.
Could you please leave the class and join again? Is it better now?
No, I can't see it. Oh, only the black page and nothing. Now I can see when you back from the screen, I can see the name of the students, but if you open the screen, I can't see anything.
I don't know what to do. Can you see now? Okay. Okay, the reduction factor I'm talking about, if you want you can check from your book. I want to talk about here in the reduction factor method for granular soil. As I said, this method can be used for just granular soil. And when you have clay or when C is zero, when you have clay or other types or a combination of clay and sand, you can use this and you can use just effective variable. But for granular soil, you can use reduction factor method and take and notice that I don't need this chapter, this part. So where is my pen here? So this method is not required. Just effective area and reduction factor. Okay. It says that instead of changing the width of the foundation, you can go as normal and find your capacity, but at the end, you should reduce the capacity. Okay, so you treat the foundation, you treat an eccentric foundation as before. So, for example, the loading is not in the center. You treat it as before, but at the end, you use a reduction factor as reduction factors called R. R is alpha or A dot E over B power K. What are what are E is eccentricity. You all know that already. And K, what are A and K? These parameters can be obtained by this table. Okay, table 4.9. For table 4.9, by table 4.9, depends on your E over B. you can go through this table and get your answer. And if for example, d over b is, for example, point, I don't know, 0.75, it's not in the table. So you should use interpolation, or for example, you should use average. Okay. Um, you can see it here. One, if you use this equation, uh, your capacity, your final capacity is 1 minus RK. Let's solve an example. For example, here, the thing that we solved already. You all know that all the shape factors were 1. So you can see it here because all of them are 1. And because the foundation is continuous. So I'm working, I want to go with reduction factor method. You already know that depth factor for Q term is 1.16 and for gamma term is 1, like here, 1.16 and 1. So we continue as before to find Q, but at the end, QU is QU effective is QU dot reduction factor. What is this reduction factor? This is reduction factor R. Uh, 2E over B. Let me see. What was B? 1.5. B was 2. And 5. Let me see what's the. Oh, sorry. If you want to, you can use this table, as I said, but uh, based on several laboratory model tests, this K factor can be uh, assumed as 1 minus 2e over b. Okay, 1 minus 2e over b. So you have two options. First one, table 4.9 for R, table 4.9. But instead of uh, using table, you can use an approximate method with an acceptable approximation, and that would be this equation. So R reduction factor is 1 minus 2e over b. You can see it in this example. 1 minus 2e over b dot q. Let me summarize it again. So for effective method, I solved the example. For reduction factor method, QU was NQ Q dot NQ dot F Q shape factor, FQ depth factor, FQ inclination factor plus 1 over 2 gamma n gamma f cube f gamma shape factor, f gamma depth factor, and f gamma inclination factor. This is fun because the load is perpendicular. This one is 1 and this one is 1 as well. Because the foundation is continuous and B over L can be the same as 0, this one is again 1 and this one is again 1. Okay, we found this and this one was 1, so everything is clear. NQ and N gamma from table 4.2 and Q was gamma df. So in the reduction factor method, you're not going to use B prime, okay? You should use B. So this is your Q. At the end, the final capacity is QU dot R, reduction factor. As I said, you have two options to find R. The first one is table 4.9. This table, and use this equation. The second one is this equation. This one is much easier and much simpler. What is this equation? 1 minus 2e divided by b. Okay, so for this one, r would be 1 minus 2 dot point 2 divided by 2. Okay, what is the reduction? 0.4 divided by 2 minus 1.8. So the final capacity would be QU dot 0.8 and QU is QU dot 0.8 dot B dot L. Because the foundation is continuous, you consider it for unit length. L is 1. Any question?
Teacher, can you upload this video on YouTube also?
Okay.
Because I can see anything and I don't.
Okay. I'll upload it on YouTube. Any other question? Okay. I'm gonna continue the rest of it in the next class.